Myself, Dr. Anand Tirth B. Gudi, working as Professor and Coordinator, PG Studies, Department of Electronics and Communication Engineering, Global Academy of Technology, Bangalore. Today's topic to be discussed are realization of Boolean expressions and importance of simplification of Boolean expression before realization using logic gates. Next, realization of Boolean expression only with NAND gates by using graphical representation method. Next, realization of Boolean expression only with NOR gates by using graphical representation method. After that, finding the Boolean expression value y for the given logical circuit. Then we may be discussing small fundamental things about the half adder. Realize the Boolean expression y equal to AD plus BD. Using basic gates, it is possible for us to write like this. The first A variable is taken and the D variable is taken and B variable is made separately. So the meaning is the D is there in both the parts of the given equation. Here also we are seeing the D and here also we can see the D value. Instead of that, D value can also be given separately, but here the D value is taken from common line. So now the output of the first stage AND gate is equal to A into D, and similarly the output of the first stage, which the gate is represented in the bottom of the circuit, is B into D. Then both the multiplied values or AND values are going to be added in the OR gate. So then finally, after adding the BD from this output and AD from this, if we are going to add by using the OR gate, the output value Y exactly looks to be AD plus BD. But here the interchangeable is possible, hence we can also write the BD plus AD. With using the NAND gates, same output Y, if we want to realize with the NAND gates, then the execution is going to become like this. So first what we are going to do is we are going to double complement the Y value is equal to B into D plus AD. That value is going to be double complemented, and then we are going to solve for the equation. After solving the equation, we may be getting the value this. How? Let us see. So the value given is y is equal to AD plus BD. Now we should have to take this and should have to double complement this. So then finally our intention is to create this equation by using only NAND gates. So then after complementing this, we can, by using the De Morgan's theorem, this can be splitted into AD 1 bar, instead of this plus it is going to become dot, and BD bar, this is whole bar. So then with the NAND implementation, it is possible for us to do this. How it is possible? Let us see. So the A and D are taken here. So A and D are taken here. After that, these two inputs are made available at the input termination of one NAND gate. Then automatically output of this NAND gate is nothing but the multiplication of A and D along with the complement value. Next, to solve this B and D, I can take one value which is already available D to the another NAND gate input, and the B value may be taken. So then if we are going to add these two at the input, then this is the outcome. So here this is B. Now this value is equal to B dot D, okay, because of this complement value and complemented. Then once again one more complement is there with the multiplication value, hence these two outputs are once again taken to another NAND gate. First AND is going to multiply these two because of the presence of this NOT at the output termination of the NAND AND gate is termed as NAND, hence the output value what it is available can be rewritten as AD bar dot this BD bar, then the final this. So this we are going to represent as Y. So how we have splitted is already we know. Once again, by taking this Y is equal to A D B D this. If we are going to remove this complement, then automatically A D this dot is going to be removed, and along with that this double bar we are going to get, and B D bar is already available because of the adding this De Morgan's theorem, then double bar is going to cancel, then AD plus BD we are going to get, that is the original value of the equation what we have mentioned before applying double complement. So this is the checkpoint. This shows whatever we have done, the calculations are, and also the implementation of the given expression with the NAND gates is completed. Once again we will go to the next slide. The same equation implementation can be done with the NOR gates also, just by taking the similar kind of a double complement. Whether it is possible for us to do this, let us see. Once again we are going to take the same equation and then we are going to double bar it, but here instead of NAND we are going to call now this as NOR gate by using only the NOR gates. Now the equation is AD plus BD and we have taken double complement. Now once again this A into D this is, and this can be replaced with the dot, and BD this complement and whole complement. Once again if we are going to split this, then automatically we are going to write it is A bar or A complement plus D complement. Next this multiplication as it is we are going to keep, and then this B complement plus D complement we are going to split like this, and this complement will be there as usual. Now once again it is possible for us to split like this. So A complement plus D complement, and this complement if you are going to make into two parts, then this dot can be rewritten as plus. So internally B complement, D complement, and this complement is there. So in this we are saying in this equation Y, this is also added value is complemented, here also the addition value is complemented, means these two equations can be once again it can be implemented with the help of NOR gate. So once again if we should have to make it proper, because once again our intention is to cancel these two. So let us see how whether it is possible like this. So one complement we are going to create with the NOR gate. This is the NOR gate. So for this NOR gate first we are going to add this added value, then this is going to be added, and after that we are going to write. Similarly this equation is already executed, and we can come back and we can see here one A is complemented here, and D is also complemented, and B is also complemented. Such AD we are going to get a AD value here and BD value here. AD plus BD complemented value is once again it is AD plus BD. So here it is AD plus BD is complemented. Once again if you are going to complement the double complement, we are going to get cancelled, and then it is going to become AD dot AD plus BD. The original equation is found. So next, the realization of the Boolean expression, here equation y is given as A plus B into D. So this equation can be represented with the normal all logical gates. Just by using the basic gates it can be implemented like this. So A plus B, that can be implemented with the OR gate. One input is A, another input is B. So the output of this gate is nothing but A plus B. After that the D is also going to be added to this, then output of the AND gate is exactly the multiplication of A plus B into D. So that is given in the Y equation at the end of this circuit. So now if the same equation if you want to implement with the NAND gate, then once again we should have to take the double complement of A plus B into D. So under that condition, if we are going to double complement, then what happens? Let us see and execute the NAND operation with the given equation. So again it is NAND operation using only this NAND gate. The expression y is equal to A plus B into D. So now here we are going to make the double complement, then this first complement if we are going to cancel, then this becomes A into B, this part A into B, this complement plus this D complement, and the whole complement will be there. So if we are going to cancel this, then automatically this becomes A B, this complement value plus D complement, and this dot, this is going to become dot, and this is double complemented and this is double complemented. So A B double bar A B complement, and once again this is going to be complemented is nothing but A into B dot D. So this implementation, okay, is nothing is, this can also be converted. Here it is possible, here itself see this is there. So then at this stage you can stop and you can write the circuit this one also. So let us see how this can be implemented. So here by taking the complement value, it is A dot double bar and A plus B, this is there, and here the double complement we are going to make here, because it does send, it is not possible for us to conclude, and double complement if we are going to do, then automatically A plus B dot double complement, the double complement value is going to cancel, and once again we are going to get the original equation. So the next one, same equation if you want to implement with the NOR gate, then double complement of this can be done. After that we are going to use only the NOR gates. Here A plus B bar we are going to get, and also the D bar we are going to get with a plus sign here, the first complement is cancelled. After that because it is plus is here, then A plus B whatever we are going to get here, that D complemented value is going to be added and that is going to be complemented. So therefore once again we are going to get the output y is equal to A plus B into D. So the next one is realize the Boolean expression, that is y is equal to A plus A bar B. So here by using the logic gates, any logic gate, either it may be a universal gate or it may be a basic logic gate, just by using the combinations of logic gates, this is the execution of or a realization of the given expression y. So first A is there, so A is as it is it is taken to the OR because plus is there, and this part of the equation first we want to execute, that is nothing but A is complemented, and after that B is also taken and the multiplication value A bar dot B is generated. After that this plus operation or the OR operation is taken, then from this first initial point the A has been taken, and then final Y is equal to A plus A bar B can be generated like this. Another expression, so here the number of variables are A, B, C, but the complement values of those variables are also there in the equation. So usually these are all product terms, and such product values are going to be added here. So therefore for each product value we are going to develop an independent circuit, and this is one independent circuit for this execution, one independent circuit for this execution, also one independent circuit, and for this execution also we are going to make one independent circuit. After making all the realization of individual execution, then because of this addition mark what we are seeing here, OR operation may be conducted. So therefore, but here 4 input OR gate is used. So then the complement value, so the A, B, C is there here, A, B, C, all the 3 are connected to the AND gate, and here 3 input AND gate is considered. The output is the multiplication of all the 3 variables. So therefore it is A into B into C that satisfies the first part of our equation Y. And come to the next part, here A complement, B and C are there. So previously, before going to add the A value into this line of this particular AND gate, that must be complemented by using the NOT gate. That is why the NOT gate symbol is also given here, because in this case B is not complemented in any part of the equation, only the A complement is there and also C complement is there. To achieve the complement values of A and C, we are going to use 2 NOT gates. By that A bar what we are achieving through the NOT gate is fed to this line. So therefore A bar and B and C are nothing but the inputs for this particular AND gate. Hence the AND gate, 3 input AND gate output is A bar B into C. Similarly the third part of the equation is A into C. So A is taken as it is, and C is taken from the line C from the initial point, and then it is going to be multiplied in the AND gate, but here AND gate is having only 2 input termination and 1 output termination. Such AC is generated through this AND. And last equation is A complement C, then the complement value is going to be generated through this NOT gate. So this NOT gate output C bar is connected here, A is taken from the initial point of the A from here, and then these 2 are fed, and finally the AND gate output is nothing but the multiplication of A into or A and complement value C. So now to achieve this addition operation, 4 input OR gate is taken, and all the outputs of individual gates are connected to this input termination, and finally Y at the output of OR gate is seen as Y is equal to A B C plus A bar B C plus A C plus A C bar. Similarly, another simple equation is given here, that is Y is equal to B C plus A. So here A is independently taken, and first this B into C, first it should be solved, and then the output of that gate must be added with this A input. So therefore B into C first we should have to achieve, that is why B variable is taken, C variable is taken, and operation is carried out, and the product value BC is considered as one input to the last stage of the circuit OR gate, and one more termination is fed with A. Then in the addition process we are going to get the value Y is equal to BC plus A. That is exactly what it is given in the equation for realization. So next, here realize the Boolean expression Y is equal to A B complement plus C D complement into A plus B. Here first we should have to solve independently the A B bar and also A plus B. After that we are going to solve this part of the equation, and then we are going to add that part with the A B bar. So for this here all basic types of gates are used, because there is no condition here, the conditions are not mentioned, like only using the not only NAND gate or and NAND gate or NOR gate conditions are not mentioned, hence we are using all basic gates. So A, B, C, D are the inputs, and because we are seeing here B bar is there, C bar is there, so irrespective whether we are going to get or not, 4 NOT gates are provided to achieve the complement of all the variables. So then A is taken as a input, and that A will continue in this line, the input, and same A is taken to the NOT gate as an input, and output of that NOT gate is treated as A complement. Similarly B is taken on the same line, it is continued, and B complement value through the NOT gate, it is continued here. Similarly C is taken as a variable on this line, and C bar is made through this NOT, and that output of the NOT is continued as C bar. Similarly D is taken as one input, and the complement value of the D is achieved through this NOT. So in these 8 lines, on these 8 lines, the variable value A bar, B bar, C bar, D and D bar are available. So by considering these lines as parallel lines, then we are going to execute the first part of this operation, A dot B complement. We have taken the A from this point and B bar from this point. Both are going to be multiplied here by using a AND gate, and the output of that AND gate is made available here for next operation, that is nothing but OR with the remaining part of the equation. First this part of the equation also must be executed. So then the C D bar, so therefore from the point C we have taken one input, and from the point D bar we have taken one input. Once again the AND operation is carried out, and the output is seen as C D bar. Once again here the last term is A plus B. So A plus B is created by taking A to the OR gate, and once again B has taken, it is B bar, of course it is B bar is taken from here, it is B bar actually, this in this equation it must be B bar. So it is B bar is taken here, then automatically these two are going to be multiplied here, that is C D bar and A plus B bar. So finally the output Y is equal to A B bar plus C D bar into A plus B bar. So this equation addition is achieved here. Here only the thing is here bar is missing, and that bar must be added to this in order to fulfill the requirement of this. Otherwise this instead of complement value we might have taken from this line B. So from here if you are going to take this, then automatically the given expression this one is fulfilled. So now this is the realization of the Boolean expression Y is equal to C D plus A B, the total complement. So here once again the similar way A B C D are taken from the parallel lines, and NOT values of A B C and D are achieved. So on these 8 lines the values of A bar, B bar and C bar, D bar are made available. So now from in order to fulfill the multiplication value here C and D, we have taken the C value from here and the D value is taken from here. So then the multiplication value of C and D is achieved here, and here from A it is taken, and from B one point is taken to the input of the AND gate, and AND gate value is considered as A into B. So CD is available here, A into B is available here. Now we should have to add this, and after that we should have to complement the added value. Here we are using the NOR gate. Along with the basic gates and NOT, here one more NOR gate is used. Otherwise we might have used the OR gate operation. After that the output must be NOTed. So instead of making use of two gates, okay, here we have made use of only one gate, and CD and AB are connected to the two input terminations of the NOR gate, and output is nothing but the sum of those two input values with complement value, that is CD plus AB whole complement, that is achieved in this circuit. And once again the realization of the Boolean expression using simple logic gates, so or the basic gates. So y is equal to a bar plus b plus a bar plus b bar into c bar d. Let us see here once again the same kind of operation has seen a, b, c, d are the four variables, and not values of individual a, b, c, d are achieved here. Then on these 8 lines the a bar, b bar, c bar, d and d bar are available. So here also we should have to first make this particular thing, that is a bar plus b, and after that once again a bar plus b bar is achieved. After that this is achieved after multiplying these two, that multiplication value of these two terms are added with the first term. So therefore first individually 3 executions must be made. So therefore to achieve the first one, it is a NOR bar is taken, and from B termination the B is taken, then both are added with the help of OR gate, and a bar plus b is generated. Now once again to generate a c bar d, then complement value c bar is taken as one variable input to the AND gate, and this d is taken, and the multiplication values are c bar d. So then that is available here, and the equation a bar plus b bar, a bar is taken from the complement value here and b bar is taken from here. So both are going to be added here to achieve a bar plus b bar. So once again the since these two are multiplied and it is viewed here, so therefore to achieve the multiplication once again AND operation is carried out, and multiplication value of a bar plus b into c bar d is available here at the output of this particular AND gate. Then from one point this particular last OR gate is fed with a complement b and this equation part. So finally if we are going to add those two, then y is equal to a bar plus b plus a bar plus b bar bracket into multiplied by c complement d is achieved. So the final result of y expression can be achieved with this kind of a network of logic gates. Now importance of a simplification of Boolean expression before realization using gates. See here the value y is given as ABC plus ABC complement plus A complement C, that dash mark is also taken as complement, that already we have seen, either bar wise or this dash wise we can represent. So here now with this value directly if you are going to create or realize the Boolean expression using the logic gates, then how it can be done. So A, B, C are the 3 variables, and then those 3 variables are taken to a AND gate, and directly A into B into C can be generated. For the next part A and B are taken from here, this is A, B and C complement. So A, B are taken and C complement is also taken here. See here A is taken from this point and B is taken as a straight line, and this C value complemented through the NOT gate, and it is available at the input of the AND gate. So then this AND gate output is going to satisfy the second part of the equation, and third part of the equation is A complement C, that A complement value is achieved through the NOT gate and C is taken as it is. Then these two variable outputs are nothing but A complement C. So all the 3 independent parts, the product values are going to be added with the OR gate, and Y is generated. Here the number of gates used are 1, 2, 3, 4, 5 and 6 gates are there, and also here 2 NOT gates are available, and 3 AND gates are available, and 1 OR gate is available. Total number of gates are 6. Next, come to the second line of the equation. After simplifying the equation, what we can do here is AB is taken as common, and C and C complement is taken in the bracket, plus A complement C. Now C plus C bar can be treated as 1. So therefore with this second equation, if we are going to implement, then what happens, let us see. So if this is the condition, then also A and B and C are the 3 variables. So A, B is taken as it is A into B, and here one more termination, the C plus C bar, C and C complement values are taken, and then A complement C are also added. See here, C is taken as it is 1 input, and C complement is taken as it is 1 input, and here the OR operation has been taken place, and this C plus C bracket value is executed, and it is available on this particular output line. So now these two are going to be multiplied here. So these two are multiplied with the help of a AND gate, then this part of the equation is made available at this point. And here this is A complement value and C are taken, and they are made available here as A complement C. That A complement C is when it is going to be added with this part of the equation, which is made available here with the OR gate help, then automatically this output can be established. But only the thing is, here also 1, 2, 3, 4, 5, 6, 7 gates are used, because by reducing only to this extent, we are unable to minimize the number of gates. Hence this C plus C complement can be minimized, and it can be made just like 1 by using the theorems. So then automatically this C plus C bar can be made 1, then AB into A complement C. If further it is not possible for us to reduce, hence we are going to write the equation realization for this particular equation, simplified version. Then we are going to see here AB plus A complement C. AB is taken and it is made available here, and this complement value of A and along with the C, it is made available here, and finally these two equations products are going to be added here to create the output Y. And finally, even though here whatever the number of gates are less, the equation value is unaltered. Whatever the Y, the first equation value, that is even though it is reduced like this also, the equation value is unaltered, and finally if you are going to execute also, the equation value is unaltered. But here without altering the value of the equation Y, here we can execute with only 4 gates. So by simplifying the given expression, we can minimize the number of gates when it comes to realization of the given expression. So next, the realization of the Boolean expression only with the NAND gates by using graphical representation method. Then here, if we are going to see the first step of the operation, write the logic diagram for the given Boolean expression using the logic gates, that is using AND, OR and NOT gates. After that, insert the bubble at the output side of the AND gate and at the input of the OR gate. After that, replace each bubble by NOT gate. If there are double inverters, eliminate the double inverter. Finally, replace all the gates by NAND gates. These 4 points to be kept in remembrance when you are going to operate this particular NAND gate operation. So see here. So before that, it is also possible to discuss few more things that we will take up later. So that is the fundamentals. That fundamental we will see later, and now we can concentrate here. The given equation is AB plus C. That AB plus C is implemented by using very basic gates like A into B plus C is taken here, and OR gate help is taken. So what the first point says is, if your intention is to create this logic realization with only using the NAND, then in this particular circuit which is created with the basic gates, wherever the AND gate is there, that AND gate must be added by a bubble at its output, and the OR gates are added by the bubbles at the input. After doing this, the next step, we should have to convert into NOT gates. This bubble is considered as NOT gate here, and this bubble is removed from the OR gate and it is also considered as a NOT gate, and this bubble is considered as the NOT gate. So C is coming through the NOT gate to the last stage of our realization network, and these two are the gates. So when inversion, whatever the value of input available here, if you are going to invert twice, then automatically the same value is going to be available here. Hence there is no meaning in using two series NOT gates. That's why, because of that reason, if any two series NOT gates are available in graphical representation, those gates can be eliminated. And then after eliminating that, what we should have to do is, after elimination, whatever the remaining, see here, after removal of this, only this gate is there, only this gate is there, only this gate is there. So this particular operation, okay, just we are going to replace two inputs are there, one AND gate is there. So these two inputs we are going to keep as it is, and we are going to replace this with a NAND gate, and cancellation of this is taking place. Only one OR gate is there, this OR gate is also replaced with a NAND gate, and this NOT gate is also replaced with a NAND gate. The input is only one terminal, because if you are using two terminal input NAND gate, the two input terminations are shorted and it is connected to the A, and only one single output is connected to this termination, that we are seeing in the next. So here all the three, this NOT gate and AND gate and the final OR gate, all the three remaining gates, whatever after cancellation of the inverter gates, whatever the circuit is there, all components of the or logic gates of the circuits must be replaced by NAND gate. So then the equation of Y becomes A dot B complement, because here also the dot is there, okay, C bar is there, and this complement. So automatically if you are going to split this into, okay, like this, then by removing this dot, by cancelling this complement, we can write it as A dot B double complement plus C double complement. So A double complement can be once again read it as AB, and C complement can be read it as C only. So the given expression Y is equal to AB plus C has been implemented thoroughly by using only NAND gates. But instead of starting from complement by taking the Y double complement, we have not started here, we have done this execution through the graphical representation method. Next, the realization of the Boolean expression only with NOR gates by using graphical representation method. So here by using only NOR gates, the given expression must be implemented. Therefore the first point what it tells, write the logic diagram for the given Boolean expression using basic gates, that is using AND or NOT gates, and further insert the bubble at the output side of the OR gate, and how many NAND gates are going to be appear in the circuit. For all NAND gates, the bubbles must be added at the input side. After that, the bubbles are going to be replaced by the NOT gates. Then any time on the series, in the series, so two NOT gates are going to come, then the two NOT gates are going to be eliminated. After that finally whatever, after cancelling the NOR gates, if that is by seeing the condition, if whatever the final circuit is going to remain, that circuit all logical gates must be replaced by a NOR gate successfully. That is going to be the realization of the given Boolean expression with NOR gates. So here this is the equation what we have given. So here the Y value is equal to AB plus C complement. So here as per the NOR implementation, what we say is output of the OR gate, must be added by a bubble, and AND gates inputs are added with the bubbles. So that implementation is done in the second level. So now this NOT bubble in the next stage we are replacing with a NOT gate, and this bubble is also replaced with the NOT gate, and this bubble is also replaced with the NOT gate. Such a circuit we are going to see here now. So here these two inputs are replaced with NOT gate, and C so already one NOT gate is there because it is a C bar, and these last is also replaced, bubble is also replaced by a NOT gate. After that, here we are not seeing any two NOT gates coming in series in any one of these lines. So therefore these NOT gates are retained as it is inevitably. So now what we should have to do, each logical component or the device must be replaced by NOR gate. So this NOT first one A, which is going to be complemented to A bar, that is successfully replaced by a NOR gate. Similarly B, which is going to be complemented as B bar, that part is also efficiently one input. Okay, here one input is there, that's why two inputs of the OR gate are shorted, and there is a made one provision for the input, one terminal, and that is giving B bar, and the C is going to be the C bar. If all these two inputs are connected here, and this device is also replaced, logical gate is replaced by a NOR gate, and finally this is also replaced by NOR gate, finally this NOT gate is also replaced by this gate. So finally what we are going to get is A dot B plus C complement double bar. Till here we are going to get AB plus C complement and whole complement bar we are seeing here. So once again this equation is fed as a single input to this NOR gate. The output is a complemented value of that equation. Therefore AB plus C bar double bar we are seeing. So double bar is going to cancel each other automatically, then automatically the remaining part of the equation is AB plus C bar that we are seeing here. That is the one which we want to implement. Next, here few examples for simplification we have given. That is the importance here. What we have understood, the importance of the simplification of Boolean expression. So if the value of the expression Q as x bar y bar z bar plus x bar y bar z plus x bar y bar plus x y bar, if this is the given expression for y, then automatically it is to implement this kind of equation we may need many number of gates. So that is why to reduce the number of gates usage without affecting the logical value of Q, which is going to be executed by this equation, just we are going to apply the reduction method. So by taking here z common in these two expression, this xy, x bar y bar taking common, then you can write here z and here z bar. From here it is z bar and here it is taken as z. So the common factor is x bar y bar. So here and these two remains as it is. So now z plus z bar is treated as 1. Hence x bar y bar plus x bar y bar plus x y bar. So now these two are looks to be one and same. If we are taking this together, it is the same type one variable, then automatically a bar plus a bar is treated as a bar only. Like that here also we are writing one time only. So this is this together we are writing one time, that is x bar y bar, and this x y bar is taken as it is. After that here the common factor what we are seeing is y bar is looks to be common between these two part of the equation product values. So y bar is taken common and x bar plus x is there in the bracket. So x bar plus x is nothing but always equal to 1. So therefore finally Q equation may get only y bar value as a output component. So therefore after reducing these many things we are going to arrive at Q is equal to y bar. That y bar can be implemented very simply by using a NOR operation. Two inputs of the NOR gates are shorted and y is given here. So y plus y is also equal to y, NOT value is y bar. Any gate can be used here, or AND gate also can be used here for complementing the value of this y. Similarly another expressions another expression we have given here, that is ABC plus AB C bar plus A bar BC. So here 3 product terms are there, and to use to realize these 3 product terms, 3 independent circuit must be used, and afterwards to add this one more circuit must be used as a OR. So already such kind of thing we already seen in the previous slide. So now we are going to reduction, we are going to achieve here like this. A B is made common, and C plus C bar. After that this A bar BC is as it is. Now because C plus C bar is 1, then AB we are going to take here A bar BC. Then here B is common in this 2 part of this here, it is a B is common, so then B is taken as common, then from here A is taken plus A bar C is taken, then A bar C can be rewritten as A plus C. Already this we have seen in our previous sessions. So how to reduce A plus A bar C as A plus C? Then if we are going to reduce to this, then automatically this B into multiplied by A plus C can be further, it can be multiplied for our simplicity B into or A into B, it is AB and BC. So from reducing this point to this point, okay, we can reduce the number of gates, and circuit execution will also be very simpler. Anything goes wrong after rigging, for the verification also it will become very easy, and less power consumption is also there, and very small circuit can be debugged very easily, and anytime faults can be rectified. So therefore A is taken as one input and C is taken as another input for 2, and gets B input as taken as a common for both, then AB is generated here, BC are generated here, then it is going to be both the multiplication terms are added here to generate the Y equation AB plus BC. So instead of making more number of gates here, with the only 3 gates it is possible for us to realize this particular equation. Now what we were doing earlier in the all previous slides, we were given by an equation Y, and we used to reduce the expression, or we used to write the logical diagram for the given expression Y. But here what we expect here in this is Y1, Y2, Y3 we should have to find out from the given circuitry. Here 4 variables are there, and 4 variable complement values are also made available, and then what is the value of Y1? If somebody asks, then automatically it is possible for us to say like this. Let us see this B complement value is taken here, so and A is taken here, so multiplication A into that B complement value is taken, and once again that complement value is once again it is barred. Actually this let us first remove this, and we will write this is A value, is available here, and the B complement value is available here. So then the outcome is A dot B bar, this finally this is the complement value, and in this particular this one it looks to be A complement is here, A complement value, and B is made available here. The outcome is A complement value multiplication by B, and once again it is complemented. If these 2 values are taken as input, and once again the multiplication has been done, and if this is noted, then automatically what we are going to get is A B bar complement dot A bar B complement, and these values are once again complemented, this is the equation y value. So similarly here also what we can do is the B is also made available here, and C complement value is available here. So then the value is a B complement of a C and it is complemented. So here the value C is made available and value C is made available here, and value B complement is made available here, and B into B bar into C, that complement value is made here. So then y2 value may be equal to B C complement value, this is complemented, dot B bar C complement, and further after the multiplication one more complement is there, that is the value of y2. Similarly the y3 value can also be represented like this. So y3 can be implemented. Now we will go to the next slide. So here the once again we are able to generate the equation. Here exclusive OR is given. So the finally the one A is taken and B is taken, exclusive OR value, and this exclusive OR value, this exclusive OR value, finally we are able to get the y final value. So similarly here the part of the output is fed back to the exclusive OR gate. So this is also one type of a combination of a logic gate. Some part of the output is fed back to the next stage, and this stage is output is fed back to the another stage. Then y1 value is taken as one input along with C, and this y2 value is taken as a input along with D. Similarly this kind of complicated circuits can also be solved further to implement some computeral or microprocessor circuits developments. So with this we conclude our session, and next session we are going to come back with discussion of our half wave, half adder and also the full adder. Thank you.